Hi, my name is Josh Joseph, and today I'm going to be doing the Physics 2212 magnetic braking with Faraday. Now, what is the purpose of this lab? Well, in this lab, we're going to be using the results from the experiment of the falling magnet and using Faraday and using Faraday's law. Here, we're going to be comparing the experimental and computational data regarding the experiment. Now, the principles that we're going to be using are the Biot-Savart law, magnetic flux, Faraday's laws, Ohm's law, force applied on the loop, and force of gravity, which is mg. Now, for a quick overview of the results, for the experimental value, we found the observed value to be 1.297 seconds, while the computational value was 1.396 seconds. We'll go into this a little bit more later on. So for the experiment, the system was the magnet, while the surroundings was the full and everything else surrounding the magnet. The initial conditions were obviously the bar magnet, the aluminum foil that we used, the meter stick, and the magnetometer, which we used on our phone. So regarding the steps of the experiment, we first used the magnetometer app to create the north end of the magnet. Afterwards, we recorded how long it took for the magnet to fall through the tube, and repeated this process around 5 times. Now for the values, we've determined that the tube length was around zero point 0.3 meters, tube width was around 0.005 meters, the inner radius was around 0.02 meters, the mass of the magnet was 0.25 kilograms, and the magnetic dipole was 3.2 nanometers over tel. So for our trials, here are the 5 trials we conducted, and after averaging all 5 trials, we came out to around 1.297 as the time it required for the magnet to fall through the fold. Now for our checkpoint question, why can we use a Farios tube? Well, a Farios tube, which is an example could be a metal tube, would be induced by the magnet which is falling through it. This in turn causes that tube to become a magnet as well, which creates a magnetic field and causing interactions between the magnet and the pole itself, which would thus ruin the results. Now, what happens to the magnet? Well, the magnet is falling slower compared to falling in free fall because there's an additional magnetic field force acting on the magnet, and this force is acting in the opposite direction of Gravity. So by opposing the force of gravity, the effects of gravity is reduced, causing the magnet to fall slower compared to free fall. Now, for a computational experiment, as you can see, for the first two pictures I've shown, here I've just put in the initial conditions regarding the fold, the mass of the magnet, and the MU of the magnet from the lab 3. Afterwards, we're creating the function to calculate the magnetic field of the magnet, which we can see right here. Then for the rest of these pictures, we can see we're trying to create a function to create the magnetic flux and simulate the loop essentially of the magnet falling through the loop. And here finally we're just calculating the total forces acting on the magnet as well as just the velocity and position of the magnet. And here we're determining how a typical B field of a ring, and just simulating it because of how the magnet falls to the ring. Now the results computational value was 1.396 seconds, while the observed value was 1.297 seconds. A marginal difference, at least for the human eye, but statistically not too big. So interpreting the results, the intensity of the coloring, the red tube indicate the magnetic field, and the red and blue indicates current flow in the opposite directions. How do we determine which is counterclockwise and which is clockwise? Well, I determined that red is counterclockwise and blue is clockwise because when the magnet was increasing for the red and decreasing for the blue, and using right hand rule, we were able to determine the rotations. And what happens to the dynamics of the system when you flip the magnet around? The B field and induced current will flip, but everything else will remain the same. Now, how does the total time in the tube of the real world system compare to that of a computational model? As we said before, real world is very close to computational, but a computational model might be more accurate because it accounts for other factors and we can run more trials there. Now, what does the shape of the velocity versus time plot tell us about the forces acting on the bar magnet? Well, when the graph is flat, we can determine the forces are balanced out, that they're even and they cancel each other. But when the slope is represented on the graph, that means there's going to be an uneven force acting on the magnet. Now, for the errors that might have occurred in this lab, assume that the air resistance was negligible, right? We assume that the only two forces in play were magnetic and gravitational forces. We didn't take into consideration other forces, and human error, which might have occurred on my part when recording the results. Now, finally, for the what if questions regarding this lab, what if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics change? Well, the current would increase until it finally cancels the gravitational force. When these two forces even out, the magnet will stop moving. Now, what if the holes or slots were cut into the tube? How would this affect the ring current? Well, the current won't flow efficiently. There won't be a smooth flow of current. So, because of that, the force from that will be negligible compared to the gravitational force. Though it won't be a significant difference, so we won't see huge drastic changes, but they would decrease. Thank you.